I'm Ayush. So this is my first learning session. Today, I'm going to present transaction payment palette with Frank and Adam. So, main purpose of the transaction payment palette. The substrate provides the transaction payment palette for calculating and collecting fees for executing the transactions. Uh, so before coming to the pallet's main purpose, let me explain the reason behind building the transaction payment palette. So the resources which are available to a blockchain are usually limited, and it's become important to manage how on-chain operations consume them. So when any transaction happens on chain or any other activity, like the data is stored on chain, then activity changes the state of the chain and consumes blockchain resources. So as I mentioned, since the resources are limited, so we need to protect and prevent from malicious user attack. For example, a malicious user might attempt to overload the network with the messages to stop the network from producing new blocks. Then, to protect blockchain resources from being drained or overloaded, we need to manage how they are made available and how they're consumed. So the resources like memory uses, the storage input and output, uh, transition, and the block sizes. So Substrate provides several ways to manage access to these resources and to prevent individual component of the chain from consuming too much of any single resource. So there are like two most important mechanism available to the block authors. Those are weights and the transaction fees. So basically, weights uh, are used to manage the time it takes to validate a block to help ensure blocks don't consume too much execution time and like to prevent malicious users from overloading the system with unnecessary costs. Weights are generally used in the combination with transaction fees, and transaction fees are also used to make the blockchain economically sustainable because they are typically applied to transactions initiated by users and deducted before a transaction request is executed. So basically, transaction payment palette is designed to specifically handle the fee based on the weight and the length of an extrinsic. So let's see some terminology uh, to understand the concept of this palette, um, which we'll be explaining in the further slides. The base fee, this is this is a minimum amount user pay for a transaction. The wait fee is a fee basically proportional to the execution time, basically input and output and the computation that a transaction consumes. Length fee is a fee proportional to the encoded length of the transaction. A tip basically is an optional tip uh, to increase the priority of the transaction, giving it a higher chance to be included by the transaction queue. Targeted fee adjustment is basically is a kind of multiplier that can tune the final calculated transaction fee based on the network condition. So, to the next slide. Uh, Now, if we talk about the high level features of this palette, transaction payment palette provides the basic logic of calculating the inclusion fee. By inclusion fee is the basic inclusion fee is the minimum fee for a transaction to be included in a block. It also converts the weight value into a deductible fee based on the currency type using there's a config parameter weight to fee. We'll explain like when we'll work in the code base. So basically, this provides the mapping 1 unit of weight to a 1 unit of fee. So there is a function weight underscore to underscore fee, and then this weight to fee trait, basically which takes the weight as an input and then calculate the fee from the pass to weight. It also updates the multiplier of the next block based on the previous block weight using this config parameter fee multiplier update. It also uh, provides handler for managing the withdrawal, refund, and deposit of the transaction fee using this configurable parameter on charge transition. So all of the logic around the transaction fee palette is wrapped into this trait on charge transaction. This config trait like plays a very important role in calculating the actual fee. Uh, Basically, this trait has two most important function: withdraw fee and the correct and deposit fee, which like we'll explain in the further slides. Now, let's take a look at the inclusion fee. So basically, in this formula, if you see the transition fee adjustment, I already explained the base fee, length fee, these terminology in the previous slides. The transition fee adjustment is a multiplier that can tune the final fee that's based on the congestion of the network. This the inclusion fee formula basically always results in the same fee for the same input. However, like weight can be dynamic sometimes, and based on how this uh, weight to fee parameter is defined. So this one, the weight to fee is it is based on like how this weight to fee parameter is defined. The finally fee can include some degree of variability. To account for this variability, transaction payment palette provides this fee multiplier update configurable parameter. So the base fee basically like it is derived from the base weight that covers inclusion overhead like signature verifications. Length fee basically is a per byte fee that is multiplied by the length of the encoded extension. The weight fee is calculated using the two parameters, the weight fee basically extrinsic base weight and this the pallet weight annotation. So the extrinsic base weight that is declared in the runtime and applies to all the extrinsics. Pallet weight annotation that accounts for extrinsic complexity. So yeah, and just one thing important there, like the sender of a particular extrinsic is charged with this inclusion fee before the extrinsic is invoked, and the fee is deducted from the sender's balance, even if the transaction fails upon execution. Now, we talk about the dependencies. Transaction payment palette is self not dependent on any other palette, but it is a dependency of few pallets. So, for example, like pallet contract, pallet election, provider multi-phase, pallet asset transaction payment pallet. So, the pallet contract uses to fetch information about the current weight price. Pallet election provider multi-phase, it uses to estimate fee for a call. The asset transaction payment, basically it is used when you want to pay transaction fee using the custom token. So this pallet basically the asset transaction payment basically like it allows runtimes that include it to pay for the transaction in assets other than the native token of the chain. We are also covering like this palette like in this session. Adam will explain in the further slides. Talking about the high level flow. So the sign extension basically. So this extension allows you to perform logic uh, that pertains to validate the transactions received from the network or transaction pool, and also allows you to run some logic before and after extrinsic is executed. So there's a pre-dispatch method that is called uh, before a transaction is executed, and yeah, like there's a post-dispatch method which is called after a transaction is executed. So pre-dispatch basically like it has the withdraw fee, it calls the withdraw fee, and the post-dispatch basically it calls the correct and the deposit fee. So withdraw fee, this method basically is, it secures the payment uh, of the transaction fee before the transaction is executed. And the correct and the deposit fee, this method basically refund any overpaid fee and optionally deposit the corrected amount after the transaction is executed. The entry point of this function is the signed extension char transaction payment. Like we'll explain when we explain the code. The function these basically these fees and then are handed over to the this on and balance handler, so which is a injected trade function and can be configured by the runtime. Uh, so this is how it uh, looks when you submit any transactions. So if you see the highlighted part, basically this is the calculated fee. And there is also RPC interface of the transaction payment palette, which provides the RPC methods to query a dispatchable class, weights, and fee.
Yeah, I will take over here. I would like to discuss briefly an extension to transaction payment, which is called assets-tx-payment. And as Ayush already have said, it is an optional replacement which allows to pay for transactions using other fungible assets other than the native token to the chain. So this is sort of a wrapper around transaction payment palette because it doesn't redefine the transaction computation logic. What it does is it applies the logic from transaction payment palette to compute the fee, and then converts this fee into some specified asset using the fungibles adapter. User configuring this palette, developer configuring this palette to be used in a substrate runtime could provide their own implementation for this conversion, but there is a default one supplied by the assets palette, which is based on the ratio between minimum balance of the asset and the minimum balance of the native token. So if there are the same, then basically this logic assumes that the native token and this asset could be 1-to-1. And if the ratio is different, then the fees would be computed accordingly. And one important caveat is that the asset needs to be marked as sufficient for it to be eligible for transaction fee payments. And this pretty much sums up the overview of the assets transaction payment. And now I would like to show you a short demo. So if you could please. Okay, so what I will show you in this demo is two things. First part of the demo would be clicking in Polkadot.js interface as usual, and I will demo showing paying the transaction fee with assets, because I think that's more exciting than simply making a transaction and paying a fee with the native token. And in the second part, I will use the transaction payment RPC from a console, from JavaScript console. Here we have the Trappist parachain running. I think all of you should be aware of Trappist, and if not, go ahead and check it out after. It's an awesome playground parachain that we're using for all kinds of experiments. So I have Trappist running locally. And this interface is the Polkadot.js interface, but not the one hosted on Polkadot.js org, a slightly modified version. The credits for this modification goes to Frank, who hacked in support for paying transaction fees in assets. So it's not yet what you could use, but I think that should be available on the main branch soon as well. Now let's go to the assets tab. Here we can see there is an asset called learning session dollar, LSD for short, and there is an account called Bob Stash, which has 100 of LSD available. So we would like to send some LSD. Let's send it to 30. Doesn't really matter. Let's say we want to send 50 LSD. And now when I proceed to sign the transaction, a warning appears here saying that the account does not have sufficient funds to pay the transaction fee, which is correct as long as we assume that the transaction fee is paid with the chain's native currency. So yeah, without asset transaction payment, it would be not possible for this account to send any transaction. But here comes the magic button. Use an asset to pay for transaction fees, and here I could choose learning session dollar because it is a sufficient asset, and the warning disappears, and you can see that the message here has just been updated and shows that a transaction fee of some micro LSD would be applied. I will also include a tip for the block author of 1 LSD. It will not actually be 1 LSD because this is a UX issue here, right? It will be an equivalent of 1 unit of the native currency in LSD. And yeah, let's sign and submit and see what happens. Fingers crossed. Wait for the block to be finalized. And there we go. You could see that 30 has now 50 learning session dollars, and Bob has 49.999 because 50 was transferred, and some small portion was also used to pay the transaction fee. Now we will go to the Network Explorer to see the transaction fee paid event. And we could see here who authored the block. So I will copy the block author's address and now go to the Chain State Explorer. And I will check the asset balance of that account to see that it actually received the fee. So you could see here there is some balance of the asset in that account. It's 300,000, sorry. So this is because like the ratio in which native currency is converted to LSD seems to be that. But yeah, if we can get the UX correctly, that it should be like 1 LSD. But okay, this pretty much sums up the first part of my demo. And now I would like to show you some terminal. Okay, so the Node.js console. First, let's import some stuff from Polkadot.js API. Nothing interesting here. Then we create a WebSocket provider pointing to the local instance of Trappist Parachain RPC. Then we wrap it in an API promise object. Some warnings, but nothing to worry about. Let's now import some keys. These are the default, development keys. So Alice, which will be used to sign the transaction, and Bob maybe as a receiver address. So we have an API provider queuing for signing transactions, and Alice keeper. Then we have the Bob's address. So we're ready to construct a transfer. So let's try to do this. We're using API TX balances transfer. So this is like a regular transfer, not an assets transfer. Yeah, and let's transfer some money to Bob. Okay. It hasn't been transferred yet. We just created the transaction object. Now we're gonna sign it, but not send it, not yet. I mean, we're not going to send it at all. I'm just trying to show you the API for estimating transaction fee. So sign async is a nice function that retrieves all data required for signing, like the current era and the nonce for the account. And now our transaction is signed. So in order to use the RPC, we're gonna convert it to an array of bytes. U8, this is like short for unsigned 8-bit array, I believe. And yeah, let's retrieve the payment info. So for this, we're gonna call API call transaction payment API query info, and we're gonna pass this array and its length as a second argument. And we can display this info in a nice readable form by calling to human. So you can see we got the estimate for the transaction fee from the server. To get a little bit more details, we can call another method. There are two in the transaction payment API. So the other method is called query fee details, and the argument is the arguments are the same. So now let's display these details. You can see there is a breakdown of the total fee into blend fee, base fee, and adjusted weight fee. I think if you calculate it, this should sum up to the partial fee here. Seems more or less so, like 333,840 nano hop. This is more or less 1 micro hop, so 1 plus 4.7 something. This gives 5.7 something. So yeah, that's it. You can also query the RPC via Polkadot interface actually, but yeah, what I wasn't able to do with that interface is to get the encoded bytes string for a signed transaction. But I thought like doing this in the console might be a nice idea.
So these pallets were actually quite complex. So I'm trying to describe it in terms of the different components and how they fit together. Just trying to go through all the code will take quite a lot of time. So really, I was trying to sort of structure it based on initially some of the traits which were described both in the initial opening bits as well as some of the demo. So if we look at the signed extension, which is kind of where most of the magic happens, and sort of scroll down, there's kind of three notable methods. So we've got the validate function, and really that's used by the transaction queue to essentially check that a particular transaction is valid. So all that does is kind of simulates what would happen in the pre-dispatch phase. and then obviously discards the results, not committing that to the underlying state. Then we've got the pre-dispatch, and really that just does the initial charging of the fees. Then the dispatch would happen, and then finally we've got the post-dispatch, which is there. Then if we look at some of the additional traits introduced by these pallets, we've got the on-charge transaction trait. So if we dive into that, you'll see that really there's only two functions: withdraw fee, which kind of maps loosely to the pre-dispatch phase, and correct and deposit fee, which maps to the post-dispatch phase. So really it's just, allowing us to charge the fee in advance of the extrinsic being executed, and then post-dispatch doing any sort of accounting to account for any changes in the fees based on the actual fees charged versus the predicted fees in the first phase. And then similarly, the on-charge asset transaction is pretty much exactly the same. The only difference being there's an additional asset type, and then we can pass in the asset ID that's required for the withdrawal fee, etc. Interestingly enough, that parameter isn't shown on the correct and deposit fee, but it's held within the state that gets passed around. So if we just go back. So if we now look at the config traits, so really this is just a simple implementation, just a simulated. So I'm just going to kind of call out some of the more interesting bits. So we've got the on-charge transaction, which I mentioned above. And for this particular implementation, we use the currency adapter, and that's kind of the standard approach. And that uses the balances palette. And then it also uses something called deal with fees, which is how it actually takes the transaction fees and then, processes them and handles them. So in the normal node template, I think that's just a unit type. So in other words, the fees are burned. But in Polkadot and Kusama, they have this deal with fees, and that's basically just that 80-20 split between the treasury. So I'll just kind of dive into that very quickly just to show you here. So really, it's just taking the fees and rationing 80 and 20. So 80% goes to the treasury, which is down here, and then 20% to the block author. Then the next item is the operational fee multiplier, and really that just allows operational extrinsics to be prioritized within a block, and it does that by creating a virtual tip, and that's just really the final fee multiplied by whatever's configured as operational fee. The next item is the weight to fee, which is just for converting a weight to a particular fee, depending on the chain setup, or the runtime setup rather. So standard implementation, at least in the node template, is the identity fee, which does a 1 unit of weight to 1 unit of fee mapping. Whereas in .sama, they use something called a weight to fee struct, and really that's just a mapping of the base weight to 0.1%. Then the next item is the length to fee, which again is just using a one-to-one mapping here. But in the .sama setup, it's using something called a constant multiplier, and whereby it's just multiplying the length of the transaction by some transaction byte fee, which they have configured as 10 millicents. Then the last item is the fee multiplier update, and this just allows the block fee to sort of change over time depending on network usage. So a standard setup is the const fee multiplier, and for the node templates, I think it's just a multiplier of 1. So not particularly elegant. Whereas .sama uses something called slow adjusting fee update, which I'm not going to go into. Then the asset transaction payment palette config. So this is only really implemented in statements and state mine, whereas the above pallets is obviously implemented in Polkadot and Kusama. And it's fairly straightforward. Really, it's just we configure the assets pallets as the handler for the fungibles balance trait. And then the second item is the on-charge transaction handler, which I show the traits above. And really the difference being here is that we're using a fungibles adapter rather than a currency adapter above. And then as Adam mentioned in his portion, it uses that ratio of the native token minimum balance or existential deposits versus the asset minimum balance to figure out what the sort of translation ratio is. And in this instance here, I've just got it set up that all assets will be sent to the block author, just for testing. So that's the sort of high level in terms of the config. Then just to kind of go back quickly into the adapters, which is kind of where most of the logic happens. So if we just delve into the currency adapter, and then look at some of the implementation of those methods. So you see here again the pre-dispatch where we withdraw the fee. So fairly straightforward. We just determine what the reason is for withdrawal, and then we call into the currency to do the actual withdrawal, passing in who it is, what the fee is, and the reason. And then if it's successful, we get a negative imbalance that's returned. So if we just go back. Sorry, not back, go down to the post dispatch. So see here that essentially we check to see that some fee has already been withdrawn, and then we check to see if there's any refund amount due, and then we kind of just process the difference accordingly. This is then passed into the on unbalanced, which is implemented by the balances pallets, I believe. Through that handler. So not a huge amount of stuff going on here so far. So if we just go back, so that's the currency adapter. Then if we then compare that now to the fungibles adapter, which handles assets, we drop into that and then go to the same setup for the withdrawal fee. You'll kind of see here that we just call the to asset balance, which does the conversion using that ratio that I mentioned. And then once we've got that converted fee, we kind of process things in the same manner through a withdrawal on the assets pallet, well, fungibles. And then if we just quickly look at the correct and deposit fee, you can see it's doing effectively the same thing, just converting the fee. Just a sec. Right, so those are the adapters. So what we're going to look at next now is just a simulation of sort of end-to-end, kind of what Adam demoed, just how it kind of all functions in code. So in terms of the pallets themselves, as you saw in the demo, there's no real extrinsics. There's just an RPC API, the signed extension, and a hook for the first pallet. So if we just quickly look at the APIs, which you're probably familiar with, we've got the two different types of APIs. We've got the transaction payment API, which has got the query info and the query fee details, as Adam demonstrated. And then we've got the transaction payment call API. The difference being that this takes a call, whereas this takes an extrinsic. The extrinsic can be unsigned, in which case we can't charge any fees because there's no permission to do so, whereas a call always charges fees. So if we then just go back, so that's the sort of outer definition of the query API. So this little bit of code here is just kind of simulating that flow. So we take a transfer call to do some transfer of a balance, and we wrap that into an extrinsic. In this instance, I'm not signing it just for the sake of keeping the code simple. We now have an extrinsic. And that extrinsic is then passed into the transaction payment pallets query info. So that's essentially the RPC API. So we're going to delve into that quickly and kind of see how it's all set up. So you can see here that firstly it checks to see if it's signed. If it is, then we can charge a fee. If not, then there's no fee. So we'll then just see how that all kind of works. So if we go into the compute fee, you'll see that calls into compute fee details, which then calls into compute fee raw. So this is kind of the main function where the actual fee is computed, and everything else seems to kind of feed into this particular function. So you'll see here, firstly, we check to see if we're paying a fee. If not, we just return a fee details object with no inclusion fee. But if we are paying a fee based on the setup of it, we then calculate the different components that I used described in the beginning. So we firstly create the fee from the weight using the weight to fee conversion. We then get the next fee multiplier from state. We then multiply the fee by using that multiplier to get the adjusted weight fee. We also then have to calculate the fee of the length of the transaction. That's using that length to fee, which Ayush mentioned in the beginning. And then finally, we've also then got to calculate the base fee, which again, we're using the weight to fee call. Finally, once we've got all those components, we can then create our inclusion fee with that breakdown. And that's the same sort of output that, that Adam showed you earlier. So if we then just kind of go back. To the top. So that's querying the info RPC call. Then it's just a similar setup for the query fee details. So I'm not going to go into a huge amount of detail for that, but you can kind of see it's following the same path, whereby if it's not signed, don't charge, otherwise call compute fee details, which then calls compute fee raw, which is kind of, you know, where we were before. So if we just go back, then just quickly just drop into these two, you'll see these ones don't have that check as above, where we actually check to see if it's signed. So in this instance, the partial fee is always the result of the compute fee. And then the query call fee details is exactly the same. So that's essentially how we, you know, query to see exactly how much a transaction is going to cost us from the outside, and how it gets, you know, fed in and kind of tunneled all the way down to actually calculate the fee. The next area is you know, actually submitting it. So as demonstrated earlier, we've got something called the signed extension, and really what that allows us to do is to sort of tag on additional logic to handle this, the fee payments. So in this instance here, all I'm doing is just kind of creating an instance of a signed extension. So we do that by, you know, calling the from method and passing in our tip or priority fee. And then the first instance, we then kind of call validate on it. And really that's just what the transaction queue will be doing. So if we just delve into that, you'll just see that, you know, the transaction queue is calling withdraw fee and getting priority, and just kind of, you know, doing a dry run to make sure that everything would work in the same way that it would do when the actual transaction is going to be executed. If we then just kind of go back, we've then got the pre-dispatch phase, which kind of loosely maps to, you know, fee withdrawal. So if we dive into that, you'll just see here we've got withdraw fee that gets called, and then we return the results of that. The withdrawal fee, I think I mentioned in terms of the adapters. If not, I'll have to come back to it once we finish. So that's the pre-dispatch, where we effectively, you know, claim the transaction fees ahead of the dispatch. The next phase is the actual dispatch of the call, and then that kind of results in something called the post info object, as well as the result of the pre-dispatch call into the pre-object. And those two different bits of data are then passed into the post-dispatch, so that we can kind of validate everything and check to see what the fees were charged versus the actual fees versus the fees that the predicted fees which were charged in the pre-dispatch. So if we drop into that, you'll see that we basically correct the fees from those charged in the pre-dispatch to the actual charged from the post info. So we compute the actual fee from the pallet, which is there, and we take that information and we then pass that into the uncharged transaction, which is the correct and deposit fee function, which I described earlier. So that's sort of the general flow of how it works. And then the next item that the pallet offers is the onFinalize hook. And that's sort of very straightforward. You know, all it does is it just takes the current multiplier in state and then multiplies it by whatever the configured value is, and then stores that, so that when we actually calculate in the feed, that value is available and can be used between blocks. So that's the the transaction payment palette for native tokens. Then just to kind of quickly contrast it to the asset transaction payment palette. So if we kind of have a look at that palette itself, you'll see there's not a lot going on to it at all. It's just got a config trait, the pallet definition, and an event, and that's it entirely. So as Adam described, essentially it wraps around the transaction payment pallet that we described earlier. So similar setup. The difference being here is that this time we're passing in our tip and our assets, and then that asset is then stored in the state of this particular sound extension instance. And then the same thing, the same flow happens where we do the pre-dispatch to basically claim the fees. So you'll see here we've got withdraw fee. And then if we go back, we then got the actual dispatch of the extrinsic, and then we've got a post-dispatch, which then calls in to see whether it's a native token. If it is a native token, then it just literally just calls into the transaction payment to handle that, hence the wrapping. But otherwise, if it's an asset, then obviously we do something more interesting, where we calculate the actual fee and do the conversion, and then we call into the adapters, which I described earlier, and then finally emit the event. How are we doing for time? I'm not sure if I discussed the adapters in detail, but really it's just the currency adapter there and the fungibles adapter there, which kind of do, bring everything to all these little component parts together. But it's sort of due to lack of time, I think I'll stop there.
All right, great presentation, guys. Thank you, as usual.